rates because it is very practical. It kind of shows you a lot of instances where this stuff is used and how we can compare how different quantities are changing over time. We know that in general a derivative is a rate of change, right? So if I ask you, how something is changing or when it's at a maximum or minimum, we know that what we always do is find a derivative. A related rate allows us to compare more than one thing at a time. So it involves two or more quantities that change over time. The key with this, because they are rates, all of these derivatives are going to be with respect to time. So this will tie back with the implicit differentiation that we did before Christmas. You guys remember that, right? When we had x's and y's in the same problem. And so every time we did the derivative of a y, what did we put with it? dy dx, because we were doing our derivative in terms of x. So x just got to stay normal, y got a dy dx. With a related rate, we are going to do our derivative with respect to time. So time will be the thing that we do the derivative like normal. So if you have the derivative of a t, it becomes 1. But everything else we need to do with respect to time. So if I'm talking about area, when I do the derivative of area, it will be dA dt, derivative of area in terms of time. If I were doing volume, it would be dV dt. If I were talking about height, dH dt. It will all be something with respect to time. So every variable except time will have to have that rate of change with it. So our steps here. A lot of times it might be useful to draw a picture, especially if I'm talking about how a rectangle or a circle or something is changing over time. Draw yourself a picture if you can. Step 2 is the most important thing to me, and probably the thing you guys are most likely to skip. Some of you like to write everything down, some of you write very, very little down. Write down everything that you're given. Okay, I'm not talking about anybody in particular at the moment, but on a test or quiz, I will give you points just for correctly identifying all the variables that we have. Plus, it will help us tremendously when we are trying to write an equation and solve if you have a list of all the numbers that you're given. So please write down all the values of your variables and their rates of change. We'll have to use our picture to come up with some kind of an equation. Then we do the derivative with respect to t. So that's what I was saying before, everything will get a d something dt. And then at the end, we plug in our numbers. You cannot plug in your numbers before doing the derivative. Why? It wouldn't be accurate. Okay. The only numbers you could plug in before a derivative are things that don't change. Constants. What's the derivative of a constant? 0. So if you plugged in all of your numbers before, when you do your derivative, you're going to get 0. So the only numbers you can plug in at the beginning are the quantities that never change. So if I am driving a car, my position is constantly changing. So I couldn't plug that in until the very end. Okay, but if I were using a problem that involved my height, is my height changing? No, so I could plug that one in at the beginning. So constants get plugged in right away. Any quantity that's changing cannot be plugged in until the very end. And so that's what I said there. Don't substitute too early. So let's do a problem. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? What do you want to do? Write down what we have, okay? We're talking about a spherical balloon. Do you guys know what that is?
Like a 3D circle.
Yeah. So we've got this nice circular balloon here. And what's happening is we are blowing it up. So it's getting bigger and bigger and bigger as time goes on. All right. Volume increases at a rate of 100 cubic centimeters per second. Anytime your unit is a rate like this, that is talking about a derivative. It's not saying my volume is 100, that's how my volume is changing. So to denote that, we do dV for the derivative of volume, but it's in terms of time. So dV dt is 100 cubic centimeters per second. Always double check that your units are consistent. This is cubic centimeters, this is centimeters, so we're all good. But if I give you something in centimeters and something in meters, we need to make them match before we work the problem. Okay, the units, guys, give you a lot of clues about what you're looking at. Cubic centimeters, anytime something's cubed, that's volume. Second is time, so that's my dV dt. How fast is the radius increasing? So I'm talking about how the radius is changing. So I'm looking for the derivative of the radius. So dr dt is my question mark. That's the thing we are trying to find. When the diameter is 50, what's diameter? All the way across. Do I want diameter? Do I have any other mention of diameter? What do I really want from that? The radius. So what would my radius be? 25. Okay. We are talking about volume. So I need the volume of a sphere. Does anybody know volume of a sphere? 4/3 pi r cubed. I would give you that one. I wouldn't make you memorize that. And I did include a blank slide after this, I think, if you needed a little more space. So now we need to do the derivative. So the derivative of volume would be dV dt, derivative of volume in terms of time. Okay, here the 3 comes down, so 4/3 times 3 would be 4 pi r squared. You subtract 1 times. What would you have to do for the derivative of r?
dr dt.
We're doing that implicit differentiation. We're doing our derivative with respect to time. So any other variable gets d something dt. All right. We can plug in now. My dV dt was 100 equals 4 pi times 25 squared times dr dt. Okay. If I divide it by 100 on each side, just because I don't have a calculator in my hand. So to get the dr dt by itself, we would have to divide by the 25 pi. So I asked how fast the radius was changing, so that's 1/25 pi. Your units, use this, dr dt. So r was the radius, so that's centimeters. Per, t was time, what were we measuring time in? Seconds. So it's 1/25 pi centimeters per second. Why is this a positive? Increasing. If I were letting air out of my balloon, then I would expect a negative because my radius would be decreasing. Suppose that x of t and y of t are the x and y coordinates at time t of a point moving around the circle x squared plus y squared equals 25. Differentiate with respect to 25, or with respect to t, sorry. So I'm not even asking you to set up an equation this time. I gave you the equation. I want the derivative with respect to t. So that implicit differentiation. Take a second and do that one. I have to pull back what we were doing before Christmas. Derivative of x squared would be 2x dx dt, because we're doing it with respect to t, plus derivative of y squared
2y dy dt
equals derivative of 25
0.
0. So 2x dx dt equals 2y dy dt equals 0. Everything gets d something dt, whatever that variable is. Alright, so then I told you x is 3, y is 4, dx dt is 12. Find dy dt. So we have 2 times x times dx dt plus 2 times y times dy dt equals 0. So if we solve that, 6 times 12, so 72. So dy dt is -9. I didn't give you any units here. So that would be all we could put. If we think about that, it kind of makes sense that we have a negative, because we were talking about a point moving around this circle. So we were somewhere here. Since my dx dt was increasing, that means we're getting further away from x, so we had to be traveling this direction. So if you're getting further away from x, what's happening to our y? Is it getting bigger or smaller? Smaller, because your height's coming down. So it makes sense that we got a negative there. Alright. So far, so good? Next. I want you guys to take a second, see if you can read this and draw a picture. Don't try to set up anything else, just try to draw a picture. So now a rocket is being launched vertically, so it's going up. It's tracked by a radar station on the ground 3 miles from the launch site. So here's my radar station. Is this distance changing? The distance between those two. So do I need a variable, or can I just go ahead and label that as 3? We only need variables for things that are changing. Now, is the height of this rocket changing? Yes, so that would have to have a variable. So I'll call that x. What is the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles, and this distance is increasing at a rate of 5,000 miles per hour? So I'm talking about the distance between the rocket and the radar station. Is that going to change? Yeah, as it goes up, they're getting further apart. So that needs to be a variable as well. So I'll call that one y. Alright, so going back, what's the vertical speed? Speed is derivative. My vertical variable is x, so the variable for speed would be dx dt. We always do with respect to time, because we're doing rates. So that's what we're trying to find. At the instant that it's distance from the radar station, so distance from the radar station is y, is 5, And that distance is increasing. So how that's changing is the derivative. So dy dt is 5,000. All right, look at our picture. What kind of equation could we use? What do we know about triangles?
A squared plus b squared equals c squared.
Yes. Pythagorean Theorem. This is a right angle. This was going up, this was a horizontal distance. So a squared plus b squared equals c squared. Or in our terms, that would be x squared plus 3 squared equals y squared. Or you could change your 3 squared to a 9. Okay. So if we do our derivative of x squared would be 2x dx dt. What's the derivative of 9? 0, so I just dropped that. Derivative of y squared? Okay. Now when I go to plug in, I need 4 variables here. We're looking for dx dt. I have y and dy dt. I really need to know what x is, don't I? We know at the particular instant we are interested in, y is 5. So we could find x at that instant. So x squared plus 3 squared equals 5 squared. So not always, but at the instant we need, x would be 4. So then we can plug in 2 times 4, we don't know dx dt, equals 2, y is 5, dy dt is 5,000. So if we divide, what do we get? $6,250. Is that right? Units. X was measured in what? Miles. My time was measured in what on this problem? Hours. So that rocket is going up at a rate of 6,250 miles per hour. Let's do one more, and then we'll probably stop for today. Are there questions on this one? So a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So we need a picture. We have a ladder resting against a wall. So we would assume the wall and the floor make a right angle. We have this ladder here. Does the length of the ladder change? So I could go ahead and label that. It is 10. And again, the only reason I can put that 10 in there instead of a variable is because it's not changing. Now the height up and down, this stuff's going to change because what's happening is the bottom is sliding away, so it's coming down here, which makes the top of the ladder come down. So these need to be variables. because they are going to change. Doesn't matter which is which, so I'll just call the bottom x and the top y. Alright, so we know the bottom is sliding away from the wall. So the bottom is x. If I'm talking about how it's changing, that's the derivative. So dx dt is 1 foot per second. I want to know how fast the top is sliding down. So we are looking for how the top changes. So that's dy dt. When the bottom, so that's x, is 6 feet from the wall. What else am I probably going to need? Y. Could I find y for this particular instant? We could do the Pythagorean Theorem. So x is 6 squared plus y squared equals 10 squared. So y squared is 64. So y is 8 at the particular instant we're talking about. So then, our equation would be what? Y squared plus x squared equals 10 squared. So derivative of y squared would be 2y dy dt. Derivative of x squared is, okay, 10 squared is 100. What's the derivative of that? 0. So then we plug in. Y is 8. Dy dt we do not know. X is 6 and dx dt is 1. So if we divide, we get a negative 3/4. Why would this be a negative? Coming down the wall. Units. What's my y measured in? Feet. Per, what was time measured in? Seconds. So that top of the ladder is sliding down 3/4 of a foot per second. Alright. Questions so far? So we are going to spend quite a bit of time on this section. I'm just doing little by little. So we are ready for a few problems.